In the last class, we had discussed about the regulation of the blood pressure, and in the regulation of the blood pressure, we had started our discussion with the short-term mechanisms involved in the short-term regulation of blood pressure. We had also discussed that the blood pressure regulation is under three categories. One, immediate or rapid regulation of blood pressure, the intermediate regulation, and the long-term regulation. Basically, we are going to discuss about the long-term and the short-term regulation. In the short-term regulation, we had discussed in the last class about the role of the baroreceptors, where the baroreceptors are located, what are the properties of the baroreceptors, what is the range of their range in which they can maintain the blood pressure, and what is the mechanism, how they function when either the blood pressure goes up above the normal and below the normal. So in these two opposite directions, whenever the blood pressure is there, how it comes back to normal. Today we shall continue our discussion with another set of regulatory mechanisms where we find that apart from the baroreceptors, it is the chemoreceptors are also present in the body which play an important role in the regulation of blood pressure. Mind you, the baroreceptors are the receptors which help in the control of the blood pressure between 80 mmHg to 150 mmHg. Now, if the blood pressure falls below 80 mmHg, there is another mechanism that helps in bringing the blood pressure back to normal, and these are nothing but the chemoreceptors. As the word suggests, receptors are sensory structures which detect a change in the external environment. Now, what is the change which they detect? The word suggests chemoreceptors, that is the chemical changes. So what chemicals do they, changes in the chemicals do they detect? Three things they are able to detect. One, whenever there is a decrease in the oxygen concentration, that is an oxygen lack, or whenever there is a buildup of carbon dioxide, that is carbon dioxide excess, or whenever there is an increase in the hydrogen ion concentration, that is when it is becoming more acidic, or if the pH is towards the acidic side, if the pH is low. These three substances, whenever there is a change in the concentration in the blood, that is detected by these receptors and they are called as chemoreceptors. So where are these chemoreceptors present? These chemoreceptors are generally present near the baroreceptors, adjacent to the baroreceptors. Here you will find, there as a diagram you can see, this is the carotid sinus, this is the carotid body. Similarly, in the arch of the aorta also you will find that there are certain chemoreceptors which are just adjacent to the baroreceptors. The innervation is same, the vagus nerve, that is the sinus nerve here, and the herring nerves here. The main nerves which are carrying the impulses is through the vagus nerve and the glossopharyngeal nerves. Whenever there is a change in the concentration, these chemoreceptors get activated and they send signals to the vasomotor center and the cardiac center. The cardiac center and the vasomotor center in response send signals down through the sympathetic nerves and the vagus nerves to take appropriate actions. Either if there is a low blood pressure, it sees to that the blood pressure comes back to normal. Now, how is that this happens? What is the mechanism which is involved here? Now let us imagine a condition where the blood pressure has fallen down. A decrease in the blood pressure would also mean that there is a decrease in the flow of the blood. So a decreased flow of the blood will mean that there is a lack of oxygen which is happening, and the carbon dioxide which is there is getting built up in the blood because it is continuously being released from the metabolism which is taking place in the cells into the circulation. So, two things are happening simultaneously. Whenever there is a fall in the blood pressure, the oxygen concentration falls and the carbon dioxide buildup happens. That is, carbon dioxide excess happens, hypercapnia. Also, this carbon dioxide gets converted into carbonic acid which gets split into hydrogen ion and a bicarbonate ion. So, simultaneously there will be a increase in the hydrogen ion concentration, or the blood there will become more acidic, or the pH will fall. Whenever this is happening, this changes is detected by the chemoreceptors. The chemoreceptors then send signals to the vasomotor center. The vasomotor center then gets stimulated, gets activated, and the activated vasomotor center now sends signals down through the sympathetic nerves to increase the force of contraction, to increase the vasoconstriction, so that the blood pressure increases back to normal. So by this mechanism, whenever the blood pressure falls, the body sees to it that the blood pressure is restored back to normal. But this mechanism of chemoreceptor getting activated and bringing back the blood pressure to normal happens only when the blood pressure, systolic blood pressure, falls below 80 mmHg. The range of this blood pressure within which the chemoreceptors work are somewhere below 80 mmHg. So it is only in abnormal situations where the blood pressure is little low, then this mechanism comes into play. Otherwise, anything above 80 but less than 120, it is the baroreceptors which sees to it that the blood pressure comes back to normal. Now, so the range of this mechanism coming into play is only 80 mmHg systolic. It is only responsible for the chemical changes in the blood, the concentration of certain chemicals in the blood, and the concentration specifically of carbon dioxide excess, oxygen lack, or hydrogen ion excess. In addition to this, most of the walls of the arteries have certain receptors which responds to other chemicals. These receptors are the non-physiological receptors which are present in the right atrium, the right ventricle, the left ventricle, abdominal viscera, and the lungs. As the word suggests, these are non-physiologic receptors, means these receptors will get stimulated only when there is certain abnormal chemical present in the body. Now, whenever there are certain substances which are released from the damaged cardiac muscle fibers, those damaged cardiac muscle fibers release certain substances, and those substances will stimulate these chemoreceptors. Stimulation of these chemoreceptors will result in bradycardia and hypotension, and that response is known as a Bainbridge reflex. Similarly, this response or this Bainbridge reflex is seen commonly in myocardial infarction. So what happens in myocardial infarction or ischemia of the heart? There is a blockage to the blood flow in the coronary arteries. The myocardiocytes are not receiving enough oxygen. There is a ischemia happening because hypoxia happening. So less oxygen to the cardiac muscle fibers, damage to the cardiac muscle fibers. The membrane now releases certain chemical substances, and these receptors which are present will detect the presence of these abnormal chemical substances, and then they will send signals to the vasomotor center, which will result in hypotension and bradycardia. Bradycardia is a slow heart rate. So this is another reflex which is seen within the heart, especially in abnormal conditions. Similarly, there are certain reflexes, certain receptors which are present in the lungs which get activated when there is a damage to the alveolar walls or to the epithelium which is lining the lungs, the alveoli. So this reflex is known as the pulmonary chemoreflex or the pulmonary chemoreflex. It is commonly seen when there is a pulmonary embolism. So what happens in pulmonary embolism? There the vessels are getting blocked because of the blood clots being present there. As a result of which the circulation is blocked, oxygen supply to the alveoli is blocked. When there is a decreased oxygen supply to the alveolar wall or to the alveolar cells, there is a damage, inflammatory response, and that releases certain chemicals. These released chemicals, which are normally not present and will be released only when there is a damage or some pathological changes which are happening, they will stimulate these chemoreceptors, and the chemoreceptors will then cause a response by causing a bradycardia and hypotension. So apart from the chemoreceptors, there are certain non-physiological chemoreceptors which get activated only in pathological conditions. The various substances which can be seen or which can stimulate these chemoreceptors are viratidine, nicotine, prostaglandins, bradykinin and fluoride. Mind you, these are the substances which are normally not released outside the cells, they are present confined within the cell, but whenever there is a damage occurring either in the heart or in the lungs, these substances are released out of the cells into the extracellular fluid there, into the tissue fluid surrounding, which will then stimulate the chemoreceptors, and those chemoreceptors in effect will result by causing a response of either vasodilatation, severe vasodilatation will be occurring, bradycardia will be there, and hypotension. Now, what are the other baroreceptor reflexes which are taking part in the regulation of the blood pressure? Among them, one of them is the abdominal compression reflex. We have got the atrial baroreceptor reflex, the pulmonary baroreceptor reflex, the Bainbridge reflex, and the Mary's law. Now, what is abdominal compression reflex? Now, abdominal compression reflex is working something like this. Whenever there is a fall in the blood pressure, there is a sympathetic stimulation. This sympathetic stimulation will cause the increased tone of the skeletal muscle fibers. We know that the abdominal muscle is mostly comprising of the muscular wall. So, a lot of vascular supply is there on the abdominal muscles, and once there is a sympathetic stimulation is happening, as a part of the sympathetic response, the tone of the abdominal muscles will increase. That means the abdominal wall will become tightened. Rigidity will be seen, or tightening of the abdominal wall will be seen. Because of this tightening of the abdominal wall due to sympathetic stimulation, there will be a movement of the blood from these reservoirs, from the muscle mass into the circulation. As a result of which you will find that there is more amount of blood entering into the circulation, and the venous return increases, the blood pressure comes back to normal. So, this is called as a abdominal compression reflex. This is also a reflex which helps in bringing back the blood pressure to normal whenever there is a fall. Also, this abdominal compression reflex can also be seen in persons who are doing regular exercise. You would have noticed that the abdominal wall is a little tightened up in persons who are doing regular exercises. So, what does this tightening means? The tightening means that there is an increased tone of the abdominal muscles. When there is an increased tone of the abdominal muscles, that means the capacity of the vessel walls or the veins of the capillaries there to restore blood is reduced, and the blood is pushed into the circulation, as a result of which you will find that the blood pressure remains normal or comes back to normal. This is a response also seen when you are doing exercises. The other three are the atrial baroreceptor reflexes, which means that there are certain receptors which are pressure sensitive receptors which are present in the wall of the left atrium. Then you have also got the pulmonary baroreceptor reflex. The pulmonary baroreceptor reflex, as it suggests, it's a reflex mechanism. Receptors are baroreceptors, that means they respond to pressure receptors, and they are present in the pulmonary area, in the pulmonary walls. So, this means that these reflexes are present in the low pressure areas. We know that there are high pressure areas and the low pressure areas within the body. The low pressure areas, the high pressure areas are the aorta and the pulmonary artery, where they are into the systemic circulation. Whereas the low pressure areas are the atrial walls, constitute the low pressure areas, plus the pulmonary area or the pulmonary vessels are also considered as the low pressure areas. Now, there are also receptors present in these areas which respond to the changes in the pressure, hence they are called as baroreceptors. Now, when does this receptors or when does this reflex comes into play? Now, basically, the receptors in the low pressure areas are more suitable to detect changes in the blood volume. Say for example, if there is an infusion of 300 or 500 ml of blood into the system, into the body. So when the blood is being infused or a fluid is being infused into the body, say by 300 to 500 ml, this causes an increase in the blood volume. Now when the blood volume increases, this increase in the blood volume will activate the pressure or receptors or the low or the baroreceptors which are present in the low pressure areas. That means the atrial stretch receptors or the atrial blood baroreceptors or the pulmonary baroreceptors will get activated because of this increased blood volume. The response of the body would be to see to it that this extra fluid or the extra volume of the blood is removed out from the body so that the homeostasis is achieved. Now what happens when there is a 300 or 500 ml of blood which is infused? This increased blood volume will cause increase in the stretch of the left atrium. The increased stretch of the left atrium will activate the low pressure receptors which are present in the walls of the left atrium. Now once these receptors are stimulated, it will cause two responses. One, it increases the release of a substance which is called as ANP or atrial natriuretic peptide. This increased release of atrial natriuretic peptide will cause increased diuresis. That means word suggests natriuresis. Natriuresis means excretion of water. So excretion of salt and water is natriuresis. Since this is coming from a receptor which is present in the atria, it is called as an atrial natriuretic peptide. So this atrial natriuretic peptide will act on the kidney and causes a decreased reabsorption of sodium and water along the nephrons. As a result of which there will be increased excretion of urine, increased volume of urine is formed, along with this excess sodium is also removed. So in this way, the increased blood volume which is there because of the increased infusion of fluid is restored back to normal by increased excretion of urine, and this mechanism is functioning via the atrial stretch receptors, release of atrial natriuretic peptide, which sees to it that there is an increased sodium and water excretion. The other method by which the same stretch receptors will respond is by causing a decreased sympathetic activity. Now whenever there is a decreased sympathetic activity, we know that the arterioles are supplied by the sympathetic nerve. There is a vasodilatation will occur when there is a decreased sympathetic activity. So there is a decreased arteriolar resistance. When there is a decrease in the arteriolar resistance, that is the afferent arteriolar resistance which is present in the glomerulus, there is dilatation taking place. When there is arteriolar dilatation taking place, more fluid is entering into the glomerulus. When more fluid is entering into the glomerulus, there is an increase in the GFR. The increased glomerular filtration will cause more movement of fluid from the circulation into the tubules. So there will be increased urine excretion and excess water will be lost by the body. Another method by which the low pressure areas respond is by decreasing the rate of antidiuretic hormone secretion. So whenever there is this stimulation of the atrial stretch receptors, it also sends signals down to the hypothalamus, and the hypothalamus sees to it that there is a decreased release of antidiuretic hormone from the posterior pituitary. A decreased release of ADH means decreased reabsorption of water. When there is decreased reabsorption of water from the renal tubules, that means more volume of urine is formed, and the excess water which is getting accumulated in the body is now excreted through the urinary mechanism. So in this way, the atrial and the pulmonary artery stretch reflexes respond to an increased blood volume. To sum it up, there is an increase in the blood volume. The low pressure receptors which are present in the atria and the pulmonary artery get stimulated. They will act in three methods. First, they will cause an increase in the secretion of the ANP from the left atrium. There will be a decreased sympathetic activity, renal sympathetic activity. Third mechanism is that they will cause a decrease in the ADH secretion. Decreased ADH secretion means decreased ADH hormone. Decreased ADH hormone means decreased reabsorption of water, excess urine formation, increased urine formation. Decreased sympathetic activity means there is a decreased sympathetic tone, decreased efferent arteriolar resistance. Decreased efferent arteriolar resistance means more amount of fluid going into the glomerulus. GFR is increased. When the GFR is increased, the filtration is increased. When the filtration of the fluid is increased, there is increased urine excretion. The third is through the atrial natriuretic peptide, which directly causes increased excretion of sodium and water. So in this way, the low pressure area receptors which are present respond to the excess volume of blood which is present and sees to it that the blood volume is restored back to normal. So this is the diagram here which is showing the atrial of the Bainbridge reflex. Here you will find that these are the stretch receptors which are present there. They are sending signals down whenever there is a stretch of the atrium. The stretch signals are carried through the nerves here. They ascend upwards, go into the vasomotor center, and from there the signals are sent down back to the various organs of the body. Now what is Bainbridge? What is the usefulness of the Bainbridge reflex? Now the Bainbridge reflex sees to it that it does not causes damming of blood in the veins, atria and the pulmonary circulation. How does this happen? Whenever there is an increase in the blood volume, the increase in the blood volume causes atrial stretches, causes the stretch of the atria. The stretch of the right atrium will cause stimulation of the vagal nerve. This will send signals down to the vasomotor center. The vasomotor center will cause by decreasing the force of contraction. Two things are happening there. It also, because the stretch of the right atrium is present, it is stretching the SA node. The SA node stretches and the stretching of the SA node causes an increase in the heart rate. So increase in the atrial pressure because of the increase in the blood volume will cause an increase in the heart rate, whereas it will decrease the contractility there. Now these are the diagrams just depicting how this Bainbridge reflex happens. So here this is the stretch receptor, they are going up into the vasomotor center, then there they are coming back, they are inhibiting, they are stimulating this SA node, so there is an increase in the heart rate here. Now here again the same diagram is repeated where not only the signals are going to the heart but they are going sending signals down into the periphery, that is into the renal arteriolar vessels, arteriolar structures where it causes vasodilatation. The size of the arterioles increase, that means there is a vasodilatation. When there is a vasodilatation, it causes increased movement of fluid from the arterioles into the outside, that is into the glomerulus. Increased filtration is taking place. When increased filtration is taking place, it causes increased urine formation. It's the same diagram. Sensors are present in the aorta, they are present in the carotid artery, they are present in the ventricle. So these are the stimulus. The stimulus is the arterial blood pressure rises. Once the arterial blood pressure rises, the sensors are present or the receptors present in the great vessels in the left ventricle. They detect these changes. Once they detect changes, they send through the glossopharyngeal nerve and the vagus nerve. When they send signals through the glossopharyngeal and the vagus nerve, they go back up to the center. The center responds through the efferent nerve. The efferent nerve is stimulation of the parasympathetic nerve, that is the vagus nerve, and the sympathetic tone is reduced. When the sympathetic tone is reduced, there is vasodilatation. When there is a vasodilatation, the peripheral resistance comes down, as a result of which the blood pressure decreases. Here, what does the parasympathetic nerves do? Stimulation of the vagus nerve will cause, stimulation of the parasympathetic nerve will cause bradycardia. When there is bradycardia, slowing of the heart rate, indirectly it reduces the cardiac output. So the arterial pressure decreases. What started off with the arterial pressure through this circulatory reflex sees to it that the arterial pressure is brought back to normal. Now there is another response which is known as the CNS Ischemic Response. Now what is the CNS Ischemic Response? The CNS Ischemic Response is the response of the brain to reduced blood flow and reduced blood pressure. If you see all these reflexes which we have discussed above just now, you will find that, let us take the baroreceptors, the chemoreceptors or the circulatory reflexes. All these reflexes are coming into play only within a range of blood pressure, and the stimulus which is causing these responses to get activated is lying outside the brain. But this CNS ischemic response is a response of the brain when the blood pressure within the cranial cavity is reduced. So for example, if the blood pressure falls to extreme low, say around the systolic blood pressure is around 50 or 60 mmHg. So at that low systolic blood pressure, where the systolic blood pressure is just 60 mmHg, you will find that the blood flow to the brain is practically very slow or sluggish. So when the blood flow is reduced in the cerebral vessels, so the cerebral circulation comes down, the oxygen supply to the brain is reduced, so this causes a hypoxia. So hypoxia of the brain will result in cerebral ischemia. When there is a cerebral ischemia happening, there is a decreased oxygen supply to the brain. Also, there is simultaneously a buildup of the carbon dioxide which is happening. So, a reduced blood pressure, reduced oxygen supply to the brain will also result in an increase in the hydrogen ion concentration and increase in the carbon dioxide buildup. Once this carbon dioxide buildup occurs within the cerebral circulation, thereby it stimulates the vasomotor center. The vasomotor center gets so powerfully stimulated that it causes intense vasoconstriction of the body, vasoconstriction of the arterioles within the body, such that the blood pressure can go up to a maximum of 200 mmHg. So once the blood pressure reaches or goes above, then the blood flow to the brain is reduced and the blood pressure comes back to normal. So that means the blood pressure comes back to normal, the oxygen supply is restored, the carbon dioxide washout takes place and a normal blood pressure is restored. But mind you, this CNS ischemic response is a response which happens only when the blood pressure falls below 60 mmHg. It doesn't get activated above 60 mmHg. Since it is the last resort which the body is trying to bring the blood pressure back to normal, it is also called as the last ditch response. So here you see the diagram here, there is a cerebral ischemia, increased carbon dioxide buildup in the blood. This stimulates the vasomotor center. Stimulation of the vasomotor center will cause increased sympathetic activity. Increased sympathetic activity means that the systolic blood pressure is brought back to normal. Now if you see in hierarchy, at every pressure level, the body has got an integrated response where at a particular pressure level, one particular reflex will get activated. The normal blood pressure is somewhere around 120 mmHg. If the blood pressure falls from 120 to 90 mmHg or 80 mmHg, it is the baroreceptors which help in bringing the blood pressure back to normal. If the baroreceptors fails and the blood pressure continues to fall down to 60 mmHg, so between 60 to 80 mmHg, it is the chemoreceptors which come into play and see that the blood pressure is brought back to normal. If the chemoreceptor response is not adequate and the blood pressure is still falling down below 60 mmHg, say around 50 or 40 mmHg of systolic, then it is the CNS ischemic response which comes into play. Since beyond this, if this response doesn't restore the blood pressure back to normal, there is no other reflex present and hence it is called as the last ditch response. This CNS ischemic response can be sustained for around 5 to 10 minutes. That means whenever this reflex gets activated, the vasoconstriction which is happening can be seen for around 5 to 10 minutes. After 10 minutes, the CNS ischemic response also fails. Then there is another type of response which is also known as the Cushing's reaction. Now what is this Cushing's reaction? Now for this Cushing's reaction to happen, you have to understand that for a normal, there are two pressures which are happening, the cerebral circulatory pressures which are there, or the cerebral pressure which is there, and the other is the pressure which is occurring within the cavities there. Now if the CNS, for some type of response, if the CNS pressure or the pressure within the brain or the intracranial pressure goes above the arterial pressure, that is the CSF pressure goes above the arterial pressure, it will constrict the flow of the blood, or it will reduce the flow of the blood within the cerebral vessels. Normally, the CSF pressure has to be less than the arterial pressure in the brain so that blood flow happens. For some reason, if the CSF pressure is above the arterial pressure, then it will restrict the movement of flow of the blood into the cranial cavities, into the brain. This response, where the cerebrovascular pressure, the CSF pressure is more than the arterial pressure, will initiate a CNS ischemic response, and this CNS ischemic response will raise the blood pressure above the CSF pressure so that the circulation to the brain is restored. This response is known as a Cushing's reaction. Remember, this Cushing's reaction and Cushing's syndrome are different things. Cushing's syndrome, don't get confused here. The Cushing's syndrome is concerned with CNS adrenal gland. Here it is a Cushing's reaction. It is a special type of CNS ischemic response, occurs only when the CSF pressure rises above the arterial pressure within the cerebral vessels. Now, with this, we will go on to the next thing, which is the intermediate term mechanisms, intermediate regulation of blood pressure. Now, two mechanisms are involved in the intermediate regulation of blood pressure. That means the regulatory mechanisms which are helping in the blood pressure come back to normal for few minutes to few hours. Two things will happen. One, there will be fluid movement shift, fluid shift, and a stress relaxation mechanism. What does this mean? Stress relaxation, if you remember in your microcirculation, it would have been told you that there is a stretch response. Whenever there is an increase in the blood pressure, the increase in the blood pressure will cause excess stretching of the vessel wall, especially in the arteries, arterioles. So when there is an extra stretch of the arterioles, there will be more amount of dilatation happening, and this will help in bringing the blood pressure down to normal. So this is known as a stress relaxation mechanism, where there is an adjustment of the blood vessel, smooth muscle, in response to change in the blood volume. The other is the fluid shift mechanism. So another mechanism which comes into play in the intermediate regulation of the blood pressure is the fluid shift mechanism. What is this fluid shift mechanism? Whenever there is an increase in the blood pressure, either because of increase in the blood volume or because of the increase in the hydrostatic pressure, the increased hydrostatic pressure will cause increased filtration of fluid from the capillaries, through the capillaries, from the capillaries into the interstitial fluid. That means the high blood pressure results in a high hydrostatic pressure. When the high hydrostatic pressure is there, it causes increased filtration of fluid from the capillaries, as a result of which there is a movement of fluid from the vessel wall into the surrounding interstitial fluid, interstitial spaces. Thus the blood volume is reduced. When the blood volume is reduced, the blood pressure comes back to normal. So this is another mechanism which comes into play and sustains the blood pressure to a normal level for a few minutes to few hours. So these two are the mechanisms which help in the intermediate regulation of blood pressure. So here is a diagram: increased extracellular fluid volume, increased blood volume. When there is increased blood volume, there is increased mean circulatory filling pressure, or there is increased venous return of the blood to the heart. There is an increased cardiac output. When there is an increased cardiac output, there is an increased arterial pressure. In addition to this, there is an increased autoregulatory mechanism where there is an increased total peripheral resistance. This will see to it that the blood pressure comes back to normal. Now let us see the long-term regulation of blood pressure. Now the long-term regulation of blood pressure is the mechanism which sees to it that the blood pressure remains normal over a long period of time, maybe over a period of days, weeks and months together. So how does the blood pressure increase, and what is the mechanism or what is the response of the body to see to it that the blood pressure remains normal over a long period of time? So let us see the role of salt in hypertension. When there is an increase in the salt intake, there is an increase in the plasma osmolality. That means the volume is remaining the same. The sodium content is increasing. When the sodium content is increasing, that means that there is an increase in the plasma osmolarity or increase in the plasma osmolality. When there is an increase in the plasma osmolality, it causes stimulation of the osmoreceptors in the hypothalamus. Stimulation of the osmoreceptors in the hypothalamus leads to stimulation of the thirst center and the stimulation of the posterior pituitary. Ultimately, this will help in excretion of the excess salt and the water which is entering into the body. This is the general role of the salt in development of hypertension. If this mechanism fails at some particular point of time, then it will lead to hypertension. Now, few definition here. The effective circulating volume is the volume that perfuses the tissues. Now, the first thing you have to remember that this increase in the circulating volume is detected by certain volume sensors. These volume sensors will then stimulate the kidney. The kidney will then respond to the increased sodium ions and the increased volume which is present in the body and sees to it that the circulating volume comes back to normal, and when it comes back to normal, the blood pressure is restored, the volume is also restored. This is called as, whenever there is an increased sodium excretion, it is known as natriuresis. Whenever there is natriuresis, there will be also, along with salt, water is also lost. So what does these volume sensors do? The volume sensors will act on the kidney to regulate the salt and water loss. An increase of the blood pressure will activate the sympathetic nerves. This sympathetic nerve activation will lead to reduced flow of blood to the kidney and hence reduce the filtration. Several hormones are released in response to the changes of the circulating volume. If the fluid volume is increased, there will be an effectively increased loss of salt and water by the kidney. Now, how does this increase in the volume causes increased excretion of salt and water? That is through two main mechanisms which are central to the long-term regulation of the blood pressure, and this is through the renin-angiotensin mechanism. So, a renin-angiotensin mechanism is the key mechanism to see to that the blood pressure remains normal over a long period of time. In addition to this, to a minor extent, it is the aldosterone and the vasopressin or the ADH will also help in regulating the salt and the water loss. So now to explain to you this renin-angiotensin mechanism, it is something like this. There is an increase in the blood pressure. This increase in the increased blood pressure will respond either in the body by acting on the kidneys and the liver through the angiotensin mechanism and see to that the blood pressure is restored back to normal. This can act in both the ways, whenever there is an increase in the blood pressure or there is a decrease in the blood pressure. Let us see what happens when there is a decrease in the blood pressure. When there is a decrease in the blood pressure, the decreased blood pressure is detected by the kidneys. In the kidneys, we know that along the tubules, there are certain nephrons which are known as the juxtaglomerular nephrons. these juxtaglomerular nephrons will see to it that, will detect that there is a decrease in the blood pressure, there is a decreased fluid flow through the tubules. Immediately, because of the decreased flow of fluid through the tubules, the prorenin will get secreted from the JG cells. The JG cells will release prorenin. This prorenin will be converted into renin. Once the renin is activated, it will enter into the circulation, and in the circulation it will act on a substrate which is known as angiotensinogen. The angiotensinogen is released from the liver. The angiotensinogen in the presence of renin gets converted into another substance which is known as angiotensin 1. This angiotensin 1 now will enter into the circulation, and within the lungs, the angiotensin converting enzyme which is present in the capillaries of the lungs will convert the angiotensin 1 into angiotensin 2. So this is the main response of the body in response to a decreased blood pressure. A decreased blood pressure being detected by the juxtaglomerular cells, the juxtaglomerular cells causing the release of prorenin converted into renin. Renin enters into the circulation, acts on the liver. In the liver, there is a angiotensinogen. This angiotensinogen is converted by renin into angiotensin 1. Angiotensin 1 enters into the lungs. In the lungs, the presence of angiotensinogen converting enzyme in the capillaries gets converted into angiotensin 2. Now this angiotensin 2 has got two effects. One, it causes an intense vasoconstriction. Second, it sees to it that there is increased excretion of salt and water. So two things you have to remember here. Angiotensin 2 acts in two ways. One, it is a very powerful vasoconstrictor. It causes vasoconstriction and restores the blood pressure back to normal. On the other hand, it will act on the kidneys itself by causing increased excretion, by causing increased water reabsorption and retention of salt. How does it do? So when this angiotensin 2 enters into the circulation, it acts on two places. One, it acts on the vessel wall or the arteries and causes vasoconstriction. It also acts on the veins and causes venoconstriction. So when there is a vasoconstriction, that is constriction of the arteries, it causes increase in the diastolic blood pressure. When it acts on the veins and causes venoconstriction, it increases the venous return to the heart and restores the blood pressure back to normal. On the other side, this angiotensin 2 will act on two ways. One, because it causes a powerful vasoconstriction, it will also cause constriction of the efferent arterioles in the kidneys. Constriction of efferent arterioles on the kidneys means that there is a reduced blood flow through the tubules. So the peritubular capillaries are now having less blood flow along the capillaries. So when there is a sluggish flow along the peritubular capillaries, there is increased reabsorption of salt and water from the peritubular capillaries. This is one method or one mode of action of angiotensin 2 on the reabsorption of salt and water through the peritubular capillaries. Secondly, when there is a efferent arteriolar vasoconstriction, that means less amount of fluid is passing through the nephrons. So when there is less amount of fluid passing through nephrons, that is there is a decreased GFR. This decreased GFR means that as the fluid is passing through the tubules, there will be an increased reabsorption of salt and water by the tubules. So this helps to restore the blood pressure back to normal. So dual action on the kidney. One, efferent arteriolar vasoconstriction causing decreased blood flow in the peritubular capillaries, causing increased reabsorptions of salt and water. Secondly, decreased GFR. Decreased GFR means decreased fluid in the nephrons, in the tubules. A decreased fluid in the tubules means direct action of the tubules of the nephrons to cause reabsorption of salt and water. The other action would be that this angiotensin 2 acts on the adrenal cortex. It causes the release of aldosterone. Aldosterone will act again on the collecting ducts and on the distal parts of the convoluted tubules, and it will cause increased reabsorption of water and salt. Thus, it sees to it that whenever there is a salt which is reabsorbed, water is also carried along with it. Plus, there is a increased reabsorption of water. So, this increased reabsorption of water will also sees to it that the blood volume is restored and the blood pressure comes back to normal. The same mechanism can be used in controlling hypertension. Just to deviate from it, the pathological changes which are involved, the pharmacology which is associated with it is, in hypertension there is a blood pressure. When there is an increased blood pressure, you can directly give drugs which are blocking the angiotensin converting enzyme, action of the angiotensin converting enzyme, which we call it as ACE inhibitors. What are ACE inhibitors? Angiotensin converting enzyme inhibitors. So, if you give a drug which blocks the release of this angiotensin converting enzymes, so there will be no such enzyme which will be available. So, there will be no conversion of angiotensin 1 to angiotensin 2. When there is no conversion of angiotensin 1 to angiotensin 2, that means less angiotensin. When the levels of the less angiotensin are less, when the amount of angiotensin is less, that means less vasoconstriction. When there is less vasoconstriction, that means the high blood pressure can come back to normal. On the kidneys also, when there is less angiotensin, decreased salt and water reabsorption. So there is increased loss of salt and water. When there is decreased loss of salt and water, that means fluid retention doesn't take place. The blood volume the extracellular fluid volume comes back to normal. So the high blood pressure can be brought back to normal. So one of the methods of intervention is you give a drug which blocks the action of angiotensin the ACE, angiotensin converting enzyme, and thus brings the blood pressure back to normal. The other mechanism by which these blood pressure drugs can act is by blocking the receptors. Say for example, if you give a drug which blocks the action of the angiotensin, that is, you give a drug which blocks the angiotensin 2 receptors, so there will be no action of the angiotensin 2 on the body. Thus, the vasoconstriction will be reduced, the reabsorption of salt and water will also be reduced, thus bringing the blood pressure back to normal. Now here this is the thing which we have been shown in the diagrammatic way. Here you will find that angiotensinogen is released. This is released from the liver. The angiotensinogen released from the liver is acted upon by the renin, which comes from the juxtaglomerular cells. This angiotensinogen gets converted into angiotensin 1. The angiotensin 1 in the capillary walls of the alveoli get converted in the presence of angiotensin converting enzyme into angiotensin 2. This angiotensin 2 then will act on the adrenal cortex. Acting on the adrenal cortex, it will cause the release of aldosterone. Aldosterone will then cause the reabsorption of sodium in water and will cause sodium retention. Angiotensin 2 can also directly act on the kidneys and show its effects. So here it is the same way in the flow chart. Decreased arterial pressure, renin is released, acts on angiotensinogen, converts into angiotensin 1, ACE, that is the angiotensin converting enzyme, converts into angiotensin 2. Angiotensin 2 may be acted upon after some time by angiotensinase and get destroyed, but its duration of action is 2 to 4 minutes. In this 2 to 4 minutes, the action it shows is it causes vasoconstriction, increases the arterial pressure, it acts on the kidney, two-way I have told you, remember, directly on the kidney and through the aldosterone mechanism, through the adrenal cortex. It causes renal retention of salt and water and increases the arterial blood pressure. So what happens? There is an increased salt intake, increased DCF volume, increased arterial pressure. When there is an increase in the arterial blood pressure, there is a decreased renin and angiotensin, decreased renal retention of salt and water, return of the extracellular fluid volume to normal, and return of the arterial pressure to normal. Here we add that what is the role of salt in increasing the blood pressure. Hence, a less salt diet as a precautionary measure will help in prevention of the blood pressure. But still, if it has happened, we can intervene here pharmacology through drugs by reducing the action of renin and angiotensin. So these are the various mechanisms which we have discussed over a period of time, last 3 classes, how the blood pressure remains normal. First, it is the baroreceptor. See the baroreceptors, the sustained action is present over seconds to minutes and hours. But again, we have got the once the baroreceptor fails, it is the chemoreceptors which will try to affect. If the chemoreceptors also fail, then it is the CNS Ischemic Response. In between these two, we have got the intermediate mechanisms coming into play. The intermediate mechanisms are over a long period of time. Here you will see that these 3 mechanisms are only for a short period of time. The intermediate mechanisms are few minutes to few hours and sometimes for 1 or 2 days. That is the intermediate relaxation, intermediate regulation. The intermediate regulation is by the stress relaxation mechanism and by the capillary fluid mechanism. Over a long period of time, you will see that it is the renin-angiotensin which is acting through the sodium and the salt retention, causing the blood pressure to be sustained over a long period of time. So this diagram will sum up the response. These 3, that is the CNS ischemic response, baroreceptors and the chemoreceptors, are for the short-term regulation of blood pressure. The stress relaxation and the capillary fluid shift, here you can see, is the intermediate regulation of blood pressure. Long-term regulation is through the angiotensin mechanism. Thank you one and all. Have a nice day.